Just hold on a minute. Yeah, I got it. What I was looking for. Okay, so I believe everybody is able to see my screen as well. So today we will continue with some more architectures of CNN. Now, within this, the first one, which we will start with, is what is called as VGG net. Okay, so just a minute. So it draws its name from the visual geometry group at Oxford, and they were the first one who actually came up with what this network is going to constitute and what it is going to be. Now, this has several variants of it. And I will start one by one and explain you exactly like how they would scale it up. So the first on the line is VGG net from Oxford Visual Geometry Group. And then that's what this VGG stands for. Okay. Now, in one of the variants, which is called as type A or VGG A. Okay, VGG A is also known as VGG11. So VGG11 has something like this. So you have 3x3 convolutions and just a minute, wait. There's one thing I had to find out, which was so say I take an input over here X, which again is the same sized as, so this is an ImageNet input. So essentially your X is 3 cross 224 cross 224. This goes into 64C 3W 1S 1P. Now I'm going to get down a tensor Z1. That Z1 belongs to, so what will be the size of Z1 under this operation? Tell me guys, what will be the size of Z1?
(64 cross 222 cross 222).
Just read through the convolution definition once again.
So 64 cross
224 cross 224.
64 cross 224 cross 224. So you have a zero padding as well. You have this thing. You cannot ignore that. And that's the reason why the size will come up to the same size. Okay. Now, after this, you have a max spool operation. So this is a max spool with 2W, 2S. So you get down Z2. And what does Z2 look like? So what will Z2 look like?
112 cross 112.
Cross 112.
Okay. So if I write it down, the complete network in one shot, then it goes something like this. You have input which passes through 64C3W1S1P, which passes through max pool 2W2S. From there it passes to 128C3W1S1P. Okay. From there again it passes to max pool 2W2S. From there on it passes through 256C3W1S1P. From there again 256C3W1S1P, and then to a max pool 2W2S. From there it passes to 512C3W1S1P, then 5112C3W1S1P, and then again to max pool 2W2S. From there again to now here, then we will be a fully connected 4096. So you have to calculate and tell me what this blank will be. Then again so now if you look over here carefully, just a minute.
Or is it 100352?
Is it how much?
100352.
10, let me see. 100.
352.
I'll have to calculate. No, to me it is coming to Oh, to me it is coming as 25088.
Sir, 25088. It should be.
For me, this is what it is coming as 25088. Okay. So now the point over here is that can you tell me how many learnable layers are over here?
11, sir.
Okay. So let us count. Uh, this is a learnable layer. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are your total number of learnable layers, which I have over here. Okay. Now the next question is, in this model, can you now tell me what is the total number of learnable, or can you actually find out the learnable parameters per layer, per learnable layer, and then can we come down to the point of total number of parameters in it? So please calculate.
So for the first one, is it 1792?
I mean, just keep on calculating. I'm also doing it. Are you guys solving or waiting for me to solve it?
Solving.
Yes, sir. Sir, I solved it, sir. I've solved it.
Okay, wait. Let me do my calculations and we'll again discuss. Okay, so this is what my calculation turns out to be.
Sir, in the bias term of the fully connected layers, shouldn't it be just one?
Why? Every output neuron will have one bias associated with it.
Uh, okay, sir.
How many output neurons are there?
4096 25088.
To what 25088? 25088 is the number of input neurons. Hey, wait. I made it wrong. That will be 409.
Yes, sir. Yes, sir.
How much is it coming?
So 132,863 double 36.
What? Tell me.
132,863 double
132
863
863
double 36.
336.
Yes.
Which is approximately equal to 133 million parameters. Now, pay a note to this. This is not a small number. It's 133 million parameters, which you got just from this singly small looking network. And the only time when it actually started getting into millions was not in the convolution layers. So in these three layers is when it got into millions, and specifically this is the one when it was into 100 million params. So most of these parameters actually started coming down because of the higher number of parameters were actually in the fully connected layer. Okay. So now what these guys wanted to do is that they wanted to extend this one in a way such that it is very modularly extendable. So essentially what I meant to say is that you will increase the depth, you will increase the number of parameters, but you would do in a way such that there is some sort of a block level symmetry over there. And then there was an like new function which was introduced, which is called as local response normalization, which I will get a bit later. So the next one, which is popular, is what is called as VGG B or what is called as VGG 13. After that came down, not after that, I mean, they just kept on proposing VGGC or what is called as VGG 16. And then came down VGG 19. Now VGG 19 is the sort of
Second is slide.
Slide.
Shift the slide.
So VGG 19 is sort of the bulkiest over there with the maximum number of parameters. Now in VGG 13, what they had done was that in the first two block sets of convolution, so in case of VGG 11, what you had is you had your input, which would go to a 64C3W1S1P. And then there would be a max pooling. But in case of VGG 13, what they were doing is like this. Like once you have this one, you again follow that by another 64C 3W1S 1P, and then you go to a max pooling with 2W 2S. Okay. Now from there, in case of VGG 11, what you had was a 128C 3W1S 1P and then a max pooling, but here you again cascade that with another 128C 3W1S 1P and then you do a max pooling. Okay, and then onwards it's the same way as it continues. So the change is two consecutive blocks. Here also two consecutive blocks are brought down. Now after that it retains its own way as it was going. So there was 256C 3W1S 1P followed by 256C 3W1S 1P, followed by max pooling with 2W 2S. And then again there was a 512C 3W1S 1P, followed by 512C 3W1S 1P, followed by max pooling by 2W 2S. That followed by 512C 3W1S 1P. And then after that, you again have that FC 4096. Now, if I ask you, like, what is going to come over here in this location? Can you tell me? And I think if somebody is clever, then you can tell me quick, very quickly.
25088.
Why do you think? Why do you think that will also be 25088?
Because the same layer is repeated like 64C3W1S1P.
Did others understand what she said?
Yes, sir.
And so essentially what you did is this layer has the same definition as this layer. The only thing which changes is for the convolution kernel over here, your tensor dimension has 3 channels because your input is 3 channels, whereas over here it will have 64 channels in the convolution kernel itself because the input dimension is 64. But other than that, the spatial dimension of this transformation, so whatever is the spatial dimension of this transformation or say tensor of the output, the same is the tensor obtained from here because you are doing it with a stride of 1 and a pad of 1 for a 3W combination over here. So essentially what comes out is that although, so whatever is the size of tensor over here, at these two places, they remain the same. Similarly, these two places will also have the same size tensor. And likewise, it does not really impact in any way the tensor size. Now, when you do all of this, you would find out that the number of parameters over here is approximately equal to 130. No, this is also approximately equal to 133. Because just for those two convolution layers, there is not major change which comes out over here. The value will not be exactly the same because there are these two blocks which come down. That's the only addition which will happen over there. But other than that, I mean, that's something which is just in the order of a few thousand. So in the part of million, it does not really impact. And that's also approximately equal to 133 million parameters, which is over here. Now from here, when you could move on to VGGC or VGG16. In case of a VGGC or a VGG16, what it was doing is it tried to repeat the same thing, but in the third block itself. So you will need like 3 more convolutional layers which have to be brought down. So now the change which comes down is something like this. So it starts from the same model as VGG13. So it is 64C, 3W, 1S, 1C.
So can you change the slides?
Then 64C. Yeah.
Sir, in VGG 13 as well as like VGG A and VGG B, in both the cases, the number of parameters ended up to be 133 million, right, sir?
Approximately, they are the same.
Yeah. So then, like, what did we achieve? Like, when we moved from one network to the other, like, what was the change?
You got a deeper network. So you were modularly increasing your depth. Your parameters did increase. They were not increasing in the order of million. That's why you did not see that change. It was still increasing by the order of 1,000.
Okay, so the only achievement was the network got deeper, right, sir?
Yes. Now, I believe you might have follow-up questions as to what was the rationale, why did they make it deeper, and all of those things.
Yes, sir.
Technically, at that point of time when VGG was getting developed, there was no such rationale or anything. I mean, people did not know how to really scale networks. Okay. Today we know how to scale networks. There are these very recent things from CVPR 20. I forgot. Was it CVPR or was it ICLR? But it was from 2019 itself when we started seeing this. 2019 is when the world was experimenting around different methods of scaling networks. So there is a method of scaling a network called as efficient net, which I'm definitely going to teach in class. So there are constraints which you can put down, like I put down a compute constraint or I put down a parameter constraint, and then how can I scale networks up and down.
Okay.
Okay, so this is one which comes out over here. So what was I doing? VGGC or VGG16. So after that, again, the next layer is still kept the same. So it is same as in VGG13. So 128C, 3W, 1S, 1P. Now from there, this is where you will see the change. Instead of getting into that max pool, I will again have a 256 sized convolution. But here, instead of doing it with 3 cross 3, we'll do it with 1 cross 1. Then comes 512. So the change which happened over here is that over the VGG 16, the change was introduction of this block, this block, this block. So you got 3 new blocks over VGG 13, and that's how you got down this VGG 16. Okay. Now you need to tell me what will be this blank over here.
Sir, same 25088.
25088?
Yes.
Now you need to look at something over here. I did a I did no padding essentially. So what was the reason that I never had any padding?
Because the width of the window is 1.
Okay. Now I have another question. The question is that if you look over here, I had a width of 1. So essentially, this was a convolution with a 1 cross 1 spatial size tensor. Now, what do I gain by doing that? Did I gain anything by doing that?
We can increase the
Scale.
value of each pixel or whatever image pixel value. Change the pixel value.
Scale stand.
Because a parameter is each value in the matrix is getting multiplied with some parameter.
So what is effectively happening over there? Effectively, what is happening in this case?
Scaling.
Scaling, or think about something more. Am I observing something with respect to the channels?
So is it acting like a brightness filter?
Now, what is a brightness filter?
As in the same color is transitioning means, like let's say we have a certain combination of a color for the 3 channels, and it's like if the 1 cross 1 channel is greater than 1, then like we can consider for that shade, for the single shade, it's going from black to white. So if it's greater than 1, it will be moving towards white. If it's less than 1, it will be moving towards black. So it will either dim out or get brightened up.
So let us look into what is the effective impact of these 1 cross 1 convolutions. So say I have this tensor over here, X, and I have a 1 cross 1 convolution kernel. This is my P. This is my P1, the first such convolution kernel. And my resultant over here is going to be something like Y1. Now what essentially happens? So you have this number of channels, which is C, which is the same as number of channels over here, which is C. So what you're going to do is at any given point in space, when you are applying this, so essentially you're going to have a dot product across the channels. So effectively what you have is there is no spatial mixing of information, because your spatial span is still restricted to 1 cross 1. So a given pixel doesn't know or doesn't operate with anything around what is there in its neighborhood. But because your span along the channel is present, so there is only channel information mixing. So essentially, you can imagine this to be something like a color transformation. So an RGB to grayscale is where you can achieve either with a weighted summation of RGBs, or you can achieve with a standard average over RGBs. Any one of them will work out fine. So one of those kind of options is something which is a channel fusion, or you can think of this as a color space conversion. So from any kind of a linear color space conversion. So from RGB I go to XYZ, or from RGB I go to YCBCR, from RGB I go down to YUV, these kind of formats. So the moment I really transform into these kind of formats, then because it's just a simple matrix operation, which goes down simple matrix transformation of every color component over there. So those are what can be implemented with a 1x1 convolution. The only difference over here is that because this is within a learning-based framework, so I'm not explicitly defining how this channel mixing is happening across it. Okay. And what I would end up getting is if I have some k number of such things, then I will get down k number of such channels. And this in total is going to be my final output tensor y, where the number of channels in my output tensor is also equal to k. Okay, so is that good? Now, in case of VGG-A or VGG-11, there is also a variant over here, a variant which is called as VGG-A LRN. Now, LRN stands for a separate layer called as local response normalization. Now, what happens in case of LRN is you don't put down LRN everywhere, but it's put down in the earlier layer. So you have input, you go down to 64C, 3W, 1S, 1P. From there, you have this LRN. And from here, you go to this max pool, 2W, 2S. From there, again, it is 128C, 3W, 1S, 1P. Then to max pool, 2W, 2S. Then comes 256C, W1S, 1P. So on and so forth for in case of VG as it is. Now, the point over here is that what is this operator local response normalization doing over here, and what does it exactly look like? So this local response normalization layer, which I have over here, this can be defined as that the output for a certain channel I at a location x comma y can be given as the input at the same location for the same channel divided by this normalization factor, which is k plus alpha times this one. So what you have over here is in this layer, there are some learnable parameters which come down over here for this particular layer, not many. So this essentially is within this tensor. This is one of this location. So this is channel number and this is the spatial coordinate. Now K, alpha, beta, these are the learnable parameters, and N is designer's choice. So essentially over how many, like what should be the span of this operation over the number of channels is something which you get over here. Now, in a way with local response normalization, also you are trying to achieve some sort of a consistency and mixing across the channels or a normalization across the channels. And that's something which you can do with a 1x1 convolution. So for deeper networks, it was realized that this local response normalization does not really play a very significant impact. The only difference which comes in that you can get a local response normalization being done with much lesser number of learnable parameters, since you have only 3 parameters per layer to learn. If you have those 1x1 convolution, then you still have more number of parameters, because if not anything, it is of the order of the number of convolution kernels multiplied by the number of channels in the input. So in case of 64, it is going to be 64 cross 64. So then that's a fun which will happen over there. Now that's a difference which comes over here. However, local response normalization being a fractional and exponential computation, it's very computationally expensive and not something which is very well liked by the community as such. Okay, so that's all what I had to say for the day. Later on in the day, you will get down instructions about setting up your PyTorch environments and everything. Tomorrow we will be having a coding tutorial, the first basics of starting with it, and then that would be on with Linet. So the standard guideline is that please install PyTorch on your local machines. We'll send you 1-2-liner instructions on MS Teams itself on what to do and get it up and ready. And we strongly do not recommend, we strongly advise against using Google Colab for doing these ones, because if all of you try to access Google Colab at the same point of time, you will not get your access sessions and then it will be very slow. And the exercises which we are doing don't require a GPU at all. So all of you can run them on the CPU. That's the point. So that's all what I had for the day. If you have any doubts, otherwise we can close it.
Hello, sir.
Yeah.
Before LRN, we were discussing the significance of the reason why we are doing that 1x1 tensor, right, sir? Convolution.
Yes. Yeah.
So can you just please repeat the reason, like what we eventually achieved?
So eventually what you are able to do is you are able to do channel mixing of information without mixing on the spatial domain. So yes, earlier what was happening? You were mixing in the spatial domain as well as in the channel domain. Over here, I don't want to mix in the spatial domain. I want to retain whatever spatial things are there, but I want to mix everything in the channel domain.
Okay, no, sir. Okay, I got this, sir. But you were telling something about RGB and YUV, sir. Like, can you please repeat that part, sir? Like,
okay, so if you can, so there are multiple color spaces in which images can be represented. There is RGB, there is HSV, there is YUV, there is YCBCR, there is XYZ, all of these things. Now, some of these are called as linear color spaces, which is if I go from RGB to XYZ, it's a linear transformation. Basically, like it's a weighted summation. Every component is a weighted summation of all the other components. So that's a linear operation what we are seeing. Now, if you have that kind of a representation, that is something which can be implemented with these kind of 1x1 convolutions. So what this is doing is this is learning to have such kind of alternate channel spaces which can be created out.
Okay. Sure.